When you look at an exam paper and see a massive, complex grid of interconnected parallelograms, the sheer volume of lines can be overwhelming. Constructing a vector path relies on a mathematically precise route that connects a specific start point to a clear endpoint. This process requires you to break the grid down into its fundamental building blocks by isolating specific geometric movements, defining them as variables, and manipulating their directions using positive and negative signs. Mastering this spatial logic provides a repeatable method to navigate the grid, ensuring every line on the page leads toward full marks. Let's start with the environment itself. This is a two-dimensional grid made entirely of identical parallelograms. A vector path is simply a set of directions that connects a start point to an end point, moving strictly along the existing edges of these shapes. To build these paths, we use two base variables. The first is vector A. This represents a movement of exactly one side length horizontally to the right. Because all the parallelograms in this grid are identical, any movement across a single horizontal edge pointing to the right is equal to A. They all share the exact same magnitude and direction. The second base variable is vector B. This represents a movement of one side length up and diagonally to the right. Just like with A, any edge on this entire grid that travels up and diagonally to the right is perfectly equal to B. By stringing these units together, you can describe any movement from one point to another on this grid using only combinations of A and B. There is a strict constraint you have to respect. Vectors A and B are defined specifically by their forward directions, right and upright. Students often lose marks by mapping a path that moves backwards against these arrows without adjusting the mathematical sign. If your path requires you to travel horizontally to the left, the exact opposite of our defined vector A, you must invert the variable. One length to the left becomes a negative A. The exact same logic applies to the diagonal. Traveling down and diagonally to the left is the direct opposite of our established vector, making it a negative B. To map any route, your procedure is simple. Count how many steps horizontally, count how many steps diagonally, check your directions, and combine the terms algebraically. Consistently catching that direction change and applying the correct negative sign is the difference between a perfectly calculated route and a navigational failure. Let's apply these rules to a standard three-part exam question. Here is our grid, along with several labeled intersection nodes. Step 1. We need to construct the path starting at point A and ending at point E. To get from A to E, we follow the horizontal edges directly to the right. We move 1, 2, 3, 4 distinct segment lengths. Since we traveled 4 units horizontally to the right, matching the positive direction of our base variable, the algebraic answer is exactly 4A. Next, we need to map a path from point G to point T. Because they don't share a single straight line, we'll break the journey into 2 legs. For the first leg, we can move up and diagonally right from G, making 2 jumps to reach an intermediate point, Q. This gives us 2B. For the second leg, we move from Q straight horizontally to the right, making 3 separate jumps to finally land on T. That gives us 3A. Combine those 2 separate movements together, and the complete simplified expression for the path is 3A plus 2B. Finally, let's tackle the most complex route, navigating from point E over to point K. We start by moving up and diagonally to the right, making 2 jumps to reach point O. Because we're moving in the correct forward direction, we log a positive 2B. But from O, we have to travel horizontally to the left to reach K. That's 4 units moving in the exact opposite direction of vector A. We must log this as a negative 4A. Add the terms together, respecting the direction change, and your exact path is negative 4A plus 2B. You might spot a different physical route to get there, maybe going left first and then up. But as long as you carefully combine the horizontal and diagonal steps and fully simplify your terms, you will always arrive at the exact same algebraic expression. Looking back at our grid, we now have 3 complete, accurately solved vector paths coexisting successfully. The cardinal rule of vector navigation never changes. Identify your base variables, count the steps, and let the physical direction dictate whether you use a positive or a negative sign. When tackling these questions, scan the diagram for geometric symmetries. Because every parallelogram is identical, you can often reuse known vector lengths to shortcut your calculations. Keep the final examiner requirement in mind. While multiple physical routes are valid, your final algebraic expression must be completely simplified to earn full marks. Breaking down spatial movement into a strict, unbreakable set of procedural rules allows you to navigate the geometric plane with total accuracy.